We now learn about geometric sequences, also known as geometric progressions. And for that, we'll be working with the two sequences of numbers that we see here. And by the end of this video, we'll know what makes a sequence geometric, and we'll therefore know how to recognize a geometric sequence, and we'll also know how to find and use the formula for the nth term of any geometric sequence. So let's get started. Geometric sequences, or geometric progressions, are characterized by the fact that to get from one term to the next inside the sequence of numbers, we always multiply by the same number. For instance, looking at the first sequence of numbers we have here, as we work our way from left to right, you may notice that to get from one term to the next, we're always multiplying by 3. And that amount or number by which we're always multiplying is known as the common ratio. And we'll usually refer to the common ratio with the lowercase letter r. So for this first sequence of numbers, we would write that the common ratio r is equal to 3. Now for this sequence, finding the common ratio was quite simple. Because answering the question, what do we have to multiply 2 by to get 6, or even what do we have to multiply 6 by to get 18, is quite easy to answer. Indeed, we quickly figure out that we have to multiply by 3. But at times it won't be quite as easy to figure out what we have to multiply each term by to get to the next. And for such cases, there's an important result we need to know about the common ratio of every geometric sequence. And here it is. Given a geometric sequence, the common ratio r will always be equal to u sub n plus 1, or the n plus 1th term, divided by u sub n. And I'll go ahead and box that result. Do make a note of it. Now, if ever you find this type of notation a bit intimidating, let me quickly remind you or introduce you to the fact that each term of a sequence of numbers can be referred to using the letter u with a subscript. For the first term, that would be u sub 1. For the second term, that would be u sub 2. The third term would be u sub 3, and so on and so forth. And what this formula is telling us is that we can always find the common ratio using any pair of consecutive terms and dividing any term by the previous. So for instance, we could say that r is equal to u2 divided by u1. And so that would be 6 divided by 2, that's 6 divided by 2, which gives us 3. Or we could have taken the fourth and the third term and written that r equals to u4 divided by u3, which would give us 54 divided by 18, which again equals to 3. So this formula gives us a method for finding the common ratio by dividing any term by the previous. Now, what if I were to ask you to find the next two terms of this sequence? Well, carrying on with the progression we have here, to find the next term we would multiply 162 by 3. And you can go ahead and check, but if we multiply 162 by 3, we get 486. And that would be the 6th term. We could of course carry on and find the next term of the sequence. And once more, all we'd have to do is multiply this term, so 486, by 3. And again, you can check, but multiplying 486 by 3, I find that's equal to 1,458. And that would be the 7th term, so u sub 7. Carrying on this way, we could write all the terms of this geometric progression. In fact, the only two things we need to write every single term in a geometric sequence are the first term, so in this case u1, which equals to 2, and the common ratio, which is r equals to 3 in this case. And that again is quite an important characteristic of every geometric sequence. Provided we know what the first term is, and provided we know what the common ratio is, then we can find every single term of the sequence using the following rule. Given any term u sub n, we can find the next term, u sub n plus 1, by multiplying u sub n by r. And in fact, I'll box that as well. There we go. The formula I've just written here, which is known as a recursive formula, is the formula you would enter in a spreadsheet to write as many terms in the geometric sequence that you needed. All we would have to write is the value of the first term, u1, and then we would find the next term, u2, by multiplying u1 by r. Then we'd find the next term, u3, by multiplying u2 by r, and so on and so forth. But without a spreadsheet, what if I were to ask you what's the 15th term of this sequence? Or even, what's the 50th or what's the 100th term of this sequence? Well, one way to answer that would be to use this result and work our way up to the term we needed, but that would definitely be time-consuming. Luckily for us though, every single geometric sequence also has a formula which allows us to calculate any term we need directly. And here it is. The nth term of a geometric sequence is given by u sub 1, so that's the first term, times the common ratio r raised to the power of n minus 1. And I'll go ahead and box that. Do make a note of this formula. That's the formula for the nth term of a geometric sequence. And I'll just write formula for nth term. And what's quite important to notice here is that given a geometric sequence, all we'll need to fully define a formula that lets us calculate any term we need is the first term of the sequence, u sub 1, and its common ratio r. And for the geometric progression we had here, the first term was 2, and the common ratio was 3. So copying this formula and replacing u1 by 2 and r by 3, we get u sub n equals to 2 times 3 raised to the power of n minus 1. And that's this sequence's formula. And here's how to use it. Let's say I want to calculate the fifth term of the sequence. Then all I'd have to do is replace every n I see inside this formula by 5. And so that would be u sub 5 equals to 2 times 3 raised to the power of 5 minus 1. That's equal to 2 times 3 raised to the power of 4. And since 3 to the power of 4 is 81, this turns into 2 times 81. Finally, we can state that the fifth term, u sub 5, equals to 2 times 81, which is 162. Done. And here we could actually check that this answer is correct because we were given the fifth term of the geometric sequence. And indeed, it was 162. And again, we could use this to calculate any term we wanted. Say I wanted to find the 15th term in this geometric progression. Then again, I'd go back to my formula here and replace every n that I see by 15. And that would be u sub 15 equals to 2 times 3 raised to the power of 15 minus 1. That becomes 2 times 3 raised to the power of 14. And by all means check, but with my calculator, I find that that equals to 9,565,938. Done. Okay, now we've already seen quite a bit here. Indeed, we've seen that every geometric sequence or geometric progression is characterized by the fact that to get from any one term to the next, we always multiply by the same number. That number is known as the common ratio, and can always be found with the formula we see here. Remember, this states that r is equal to any term in the sequence divided by the previous term. And we've also seen that every term inside a geometric progression could be calculated with either one of these two formula. Remember, the top formula here is the recursive formula. And it tells us that provided we have the first term of the sequence and the common ratio, we can always find the next term in the sequence by multiplying the term we have by r. And so we'd use this recursive formula when we need to write plenty of successive terms in our sequence. The formula for the nth term, on the other hand, allows us to quickly calculate any term we need directly. So having seen all of that, let's quickly look at the second geometric progression we have here and find its formula. As we go from left to right through the terms of this sequence, it's a little less obvious what the common ratio is. So let's use our common ratio formula to find r. Using this, we can state that r is equal to u2 divided by u1. That's the second term divided by the first term. And that's equal to 192 over 384. Now, maybe you can see what that's equal to. And if you can't, you could plug it in a calculator. But that's equal to 1 over 2, or even 0.5. But remember, we can use this formula with any two consecutive terms in our sequence. So if you don't like these larger numbers on a fraction, you could take, for instance, 48 and 24, and state that r equals to 24 over 48, which makes it a little more obvious that r equals to 1 over 2. Okay, so we now know what the common ratio is. R equals to 1 over 2. And I can quickly write times 1 over 2, times 1 over 2, and so on. Okay, now to define the formula for this geometric progression, we had seen that whether it be for the recursive formula or for the formula for the nth term, we only need two things to define the formula. Those were the common ratio, which we now have, and the first term of the sequence, u1, which in this case is 384. Using them, we can now define the formula. And I'll start with the recursive formula, for which we'd simply state that u1 is equal to 384, and then I state the rule which allows us to get from any one term to the next. So in this case, that rule would be, to find the n plus 1th term, all we have to do is multiply the nth term by the common ratio, which is 1/2. Done. That's the recursive formula for this geometric sequence. Now let's find the formula for the nth term. For that, all I have to do is copy this formula and replace u1 by the first term, so that's 384, and r by the common ratio, which is 1/2. And so that would be un equals to 384 times 1 over 2 raised to the power of n minus 1. And that's this sequence's formula for the nth term. And remember, this formula allows us to calculate any term we need inside this geometric progression directly. So say, for instance, I wanted to find the 10th term in this sequence, then all I would have to do is replace every n I see by 10. And that would lead to u sub 10, or u10, equals to 384 times 1 over 2 raised to the power of 10 minus 1. That turns into 384 times 1 over 2 raised to the power of 9, and by all means check, but with a calculator I find that u sub 10, the 10th term, is equal to 0.75. And we're done. And so that's what geometric sequences or geometric progressions are all about. They are sequences of numbers in which, to get from any one term to the next, we always multiply by the same amount, the common ratio. And provided we know the first term inside a geometric sequence and its common ratio, then we can define two formula which allow us to calculate any term inside the sequence. Those formula being a recursive formula and the formula which allows us to calculate the nth term directly. And there we go. That's it for this tutorial.